Hi everyone. Through this class, we are going to study about the bilinear transformation. The bilinear transformation is a conformal mapping that transforms the imaginary axis of S-plane into the unit circle in Z-plane only once. In this mapping, all points in left half of the S-plane are mapped inside the unit circle in the Z-plane, and all points in the right side of S-plane are mapped outside the unit circle in the Z-plane. The bilinear transformation can be linked to the trapezoidal formula for numerical integration. Any analog system is governed by a differential equation in time domain. Consider the first order differential equation of an analog system. Let d by dt of y of t equal to x of t. On integrating both sides of this equation, we get integral n minus 1 t to n of t d by dt of y of t dt equal to integral n minus 1 t to n of t x of t dt. That is y of t between n minus 1 t to nt equal to integral n minus 1 into t to nt x of t dt. Applying the limit to this left hand side, we get y of nt minus y of n minus tt equal to integral n minus 1 t to nt x of t dt. And we know that the trapezoidal rule, when the integration is approximated by two trapezoid, is integral a to b f of x dx equal to b minus a by 2 f of a plus f of b. And applying this trapezoidal rule for this right hand side, we get y of nt minus y of n minus 1t equal to t by 2 x of nt plus x of n minus 1t. And for the discrete time system, the equation, the right hand side, we can write it as t by 2 x of n plus x of n minus 1. And now we take the z transform of this equation. Z transform of y of n is y of z. Z transform of y of n minus 1 is z raised to minus 1 y of z. That is equal to t by 2 x of z plus z raised to minus 1 x of z. Now y of z is common here. So it is 1 minus z raised to minus 1 into y of z. That is equal to t by 2. We can take x of z out. So it is 1 plus z raised to minus 1 x of z. Now take this term t by 2, 1 plus z raised to minus 1 to the left hand side. So here it is 2 by t, 1 minus z raised to minus 1 by 1 plus z raised to minus 1 y of z equal to x of z. On taking Laplace transform of equation, d by dt of y of t equal to x of t, we get s y of s equal to x of s. Now compare this equation with 2 by t, 1 minus z raised to minus 1 by 1 plus z raised to minus 1 y of z equal to x of z. Now we can see that this s y of s is transformed into 2 by t, 1 minus z raised to minus 1 by 1 plus z raised to minus 1 y of z. Here this t is sampling time period. Hence, by bilinear transformation, in the S domain transfer function, if S is substituted by the term 2 by t, 1 minus z raised to minus 1 by 1 plus z raised to minus 1, the resulting transfer function will be Z domain transfer function. Next, we consider the relation between analog and digital filter poles in bilinear transformation. The mapping of S-domain function to Z-domain function by bilinear transformation is a one-to-one mapping. That is, for every point in Z-plane, there is exactly one corresponding point in S-plane and vice versa. The transformation is accomplished when S equal to 2 by t, 1 minus z raised to minus 1 by 1 plus z raised to minus 1. Taking this 2 by t to left hand side, it is t by 2 s equal to 1 minus z raised to minus 1 by 1 plus z raised to minus 1. That is equal to Here take this z raised to minus 1 out from this numerator and denominator. So it is equal to z raised to minus 1 into, here this equal to 1 equal to this z. Then minus 1 divided by z raised to minus 1 into z plus 1. We can cancel this z raised to minus 1 from numerator and denominator. Therefore, t by 2 s equal to z minus 1 by z plus 1. Then cross multiplying this, here we get it as t by 2 into this s z plus 1 equal to z minus 1. That is t by 2 sz plus t by 2 s equal to z minus 1. That is t by 2 sz, then minus this z equal to minus 1 minus t by 2 s. Taking z outside, it is minus z into 1 minus t by 2 s equal to this minus out. So minus 1 plus this t by 2 s, or z equal to, here we can cancel minus and minus. So z equal to 1 plus t by 2 s by 1 minus t by 2 s. We know that z equal to 1 plus t by 2s by 1 minus t by 2s. And here Si equal to sigma I plus j omega I. Substituting that value, we get Zi equal to 1 plus t by 2 sigma I plus j omega I by 1 plus t by 2 sigma I plus j omega I, that is equal to 1 plus t by 2 sigma I plus j into t by 2 omega I divided by 1 minus t by 2 sigma I minus j into t by 2 omega I, or modulus of sigma I, that is magnitude of sigma I, equal to root of 1 plus t by 2 sigma I square plus t by 2 omega I square whole divided by 1 minus t by 2 sigma I square plus t by 2 omega I square. Now we have three different cases. First one is if our SI is less than 0. That means analog pole SI lies on the left half of the S plane. Then modulus of Z is less than 1. That is digital pole Zi will lie inside the unit circle in Z plane. Second case is if our SI equal to 0. That means analog pole SI lie on imaginary axis in S plane. Then our modulus of Zi, that is equal to 1. That is digital pole Zi will lie on the unit circle in Z plane. Third case, if Si is greater than 0. That means analog pole Si lie on the right half of the S plane. Then modulus of Zi will be greater than 1, or digital pole will lie outside the unit circle in Z plane. The stability of the filter is associated with the location of poles. We know that for a stable analog filter, the pole should lie on the left half of the S-plane. In bilinear transformation, the points on left half of the S-plane are mapped as the points inside the unit circle in Z-plane. Hence, the stability of digital filter, the digital pole should lie inside the unit circle in Z-plane. Next, we consider the relation between analog and digital frequency in bilinear transformation. For bilinear transformation, S equal to 2 by T, 1 minus Z raised to minus 1 whole divided by 1 plus Z raised to minus 1. In this equation, put S as j omega and Z as e raised to j omega. Therefore, j omega equal to 2 by t, 1 minus e raised to minus j omega by 1 plus e raised to minus j omega. In this equation, put 1 as e raised to j omega by 2 into e raised to minus j omega by 2. Now take e raised to minus j omega by 2 out. So it is equal to 2 by t e raised to minus j omega by 2 into e raised to j omega by 2 minus e raised to minus j omega by 2 whole divided by e raised to minus j omega by 2 into e raised to j omega by 2 plus e raised to minus j omega by 2. that is equal to 2 by t into, here we can cancel this e raised to minus j omega t at the numerator and denominator. Then we know that sine theta equal to e raised to j theta minus e raised to minus j theta divided by 2j, and cos theta equal to e raised to j theta plus e raised to minus j theta divided by 2. So this term in the numerator equal to 2j into sine omega by 2, and this term equal to 2 cos omega by 2. This 2 and 2 we can cancel. Then here we have one j, and at the left hand side also we have one j. Therefore omega equal to 2 by t sine omega by 2 divided by cos omega by 2. Sine by cos, it is equal to tan. Therefore omega equal to, this omega is analog frequency, that is equal to 2 by t tan omega by 2. This is digital frequency. So this is the relation between analog frequency and digital frequency. And we can derive another expression for this. From this we can see that omega is 2 by t tan omega by 2. So taking this omega to this left hand side and 2 also to this left hand side, it is omega t by 2 equal to tan omega by 2, or omega by 2 is tan inverse omega t by 2, or omega digital frequency is equal to 2 tan inverse omega by 2.